My name is Tejumade Afonja, and today we'll talk about maximum likelihood estimation and naive Bayes. Both concepts are very foundational to mastering machine learning, and it's very crucial for your journey. It would always show up in different ways, form, shape. So if today's the first time you're hearing about this or like, learning it may not be when it sticks, but you just have to continue to revisit the concept and understand the general intuition, the idea, the basic idea, why this is important, or what it is that we're actually trying to do here. Okay, just 2 topics covered today. Maximum likelihood estimation, naive Bayes, and that would take us approximately 2 hours to do so. Let's go into maximum likelihood estimation. But before we do that, we're going to start with the challenge for you. So I hope you have your computer. Of course, hopefully you're doing this on your computer, but you could also be tuning in by your phone, or I just need you to have something that you can use to calculate. But you could also be a math genius. You can do it off the top of your head. The challenge is, assume that you have some exam scores. They're drawn independently, but you do know that the distribution that those scores come from is a Gaussian normal distribution. I mean, normal, we could be using it interchangeably with Gaussian here, right? So we went through a bunch of distribution last week with MFA. So you're familiar right now that we have different kinds of distribution and they model different behavior of the data. So if you have 3 scores, you have a student, think of this as a student scores, you have 75, one student scored 75 in the exam, the other one 80, then another one 90. So my question is that, which pair of parameters do you think is a better fit? And by parameters here, because we're talking about Gaussian distribution, we mean the mean, that is the peak where the distribution peaks, the mean of the distribution, and the standard deviation, how spread the distribution is. So with these 2 statistics, the mean and standard deviation, you can model a Gaussian distribution. That's all you need. Those are the parameters it needs. So I'm now telling you that we have 2 options. There is a Gaussian that has a mean of 80 and standard deviation of 3. Another one has a mean of 85, standard deviation of 7. So which of these 2 distribution could have generated our data, which is exam score 75, 80, 90? You can just guess based on your intuition, or you can use a calculator, your computer, to try to compute it. I already gave you the mean and the standard deviation. So should be fairly easy, right? So we already have some options. Someone said B. We have 2 people that think that it should be 85, mean of 85 and standard deviation of 7. Okay, we have 3 responses. Thank you. Keep it coming, guys. You can also just guess. Okay, we have someone that thinks it's A. That is the mean of 80 and standard deviation of 3. Let's keep that thought in our head, but it's probably hard to look at numbers. So I put it out here, graphical representation. Let me know if your options have changed. So now I have those 2 distributions we just talked about verbally. The first one has a mean of 80, you can see. It peaks here at 80 and standard deviation of 3. It's a little slim. And the second one has a mean of 85 and standard deviation of 7, so it's spread out, you know. Excuse me. Now seeing it graphically, I'm asking you again, given 3 data, 75, 80, and 90, which of these two Gaussian could have generated, has the highest likelihood of generating these 3 data? I mean, they both could have generated it, but which one is more likely to have generated it? I see people changing their options. Before we had B, now we had A. Okay, this is nice. Okay, I'm sorry to tell you, but option B is correct. And we will go into what it is. So essentially, if you try to calculate it using this formula here, by plugging in the data, each of the variable x, mu, and standard deviation into the Gaussian PDF formula here, you would get the probability density shown on the y-axis here. If you can read off the probability density, you can you have an estimate for the likelihood for each of the data. So for this data, you have this estimate here. It's about 0.02. You can see that here, 75, it's about 0.02, the probability density for this point. 80 is about 0.04, and 90 is about, let's say, 0.04 something, 45. So to find the one that is like more likely, what you would want to do is to just multiply the 3 probability densities together. And if you multiply together, what you get here is higher than what you get here. And can you tell me why? By just looking at this, why do you think this is the case? Because it seems like this has higher density, right? But I'm telling you that if you look at the 3 of them together, joint, just multiply them together, this density is more likely than this one. Do you see it? Do you see why? Let's just try to read it off the graph. So what is the probability density of this 75 under this distribution? Can someone tell me? About 0.048, great. And we can do the same for 90. Okay, great. Now please multiply the 3 together. What do you get? So take the density for 75, for 80, and for 90 under this distribution and multiply it together. And then we come here, we take the density, about 0.028 or something. It's higher density here. For 80, oh, perfect. This is the peak of the distribution. It is the highest density. But what drags this down is this data point 90. The density is about 0.00. If you multiply this together, what you would get is what? An extremely small number, close to 0. And this would be less the product of this, that is multiplying the density of this would be less than this. So it means that given this distribution, these 3 data together is less likely to have been generated by this distribution than in this distribution. Does that make sense? Does that make sense? we will go into it. This is us trying to estimate. It's there now. We are given some parameters, which was what we've been doing before. We were learning parameters a few weeks ago, right? So we now say that we have this parameter. Someone said we have option A with parameter 83, mean as the division, option B, 85.7. They now said, okay, we don't know how they got this parameter. It's some oracle, we have no idea. But the question they are posing to us is that, oh, we have three data, 75, 80, and 90. Which of these two distribution can give us this data? Has a higher likelihood. This is the keyword. Is more likely. Which of these two is more likely? I mean, both of them could have generated it, but the one that is more likely to give us those three together is the option B. Is that a little bit clearer? Right? Is it? Stay with me. Okay, because this is just the beginning and we would have more math on here, but I will do my best to give the intuition. So please don't zone out just yet, because I know that it can be a little bit intimidating at first, and so, but I'll do my best. So let's go into the concept of maximum likelihood estimation. So to begin off, we are now moving away from parameters that are given to saying that we want to estimate this parameter. So we don't know. Nobody gave us this oracle. They just gave us three data points, 75, 80, 90. And they said, okay, what's your best? Like, if we want to throw away this data set and we want to just have more data, what is your best guess of this, the parameter of this data? You have to make some assumption like, oh, this data may be coming from a Gaussian. If we need to throw away those data, what is the parameter of this Gaussian distribution? And we want to learn it from the data set. It will become clearer as we go. So we are moving from probability to statistics rather. So we're computing things like the mean, like the standard deviation. We are counting, these are statistics. So the basic question here is that given some data, say data point X1, X2, X3, you could think of it as like if you have a spam classification, which we will get into a bit later. Each data point X1, X2, X3 could be the words, the different words in your email, right? The name is, those are words. So this could be like your X1, X2, X3 for each of them. But again, we'll go into this a bit more. The other one is that the question is that how do I find a distribution that captures this data well? Oh no, sorry, I misspoke a bit here. So X1 to XM it would be the first email, the second email, the third email, right? Not the words. Sorry, I misspoke. I just messed it up here. Let's keep going. We'll get clearer. So in general, if we pick from the space of all distributions, then this is a very hard question. But if we pick from a particular parameterized family, when we say, we now said that we need to pick like from a particular parameterized family of distribution. And the way we say parameterized, whenever like you see a notation like this, P of X with this colon theta. So this is just saying that this distribution here is parameterized by theta. So this is the way a lot of people denote parameterized family, just to tell you that it has some parameters. You need to learn some parameter for this data. So if we think about a particular distribution, then this question becomes easier to answer, and it becomes like, how do I find a set, like a parameter, like the parameters theta of this distribution that fits our data well? And this is the core idea of maximum likelihood. So before we start, I wanted us to do like another quiz, because we will be talking a lot about probability, and I want to make sure that you refresh your knowledge from last week, right? So what is the probability of A and B? This is a joint probability. So how do you compute the probability of A and B? Someone says it's probability of A plus probability of B. Do we all agree? A and B are not independent. Okay. Probability of A plus probability of B minus probability of A and B. All right. You're using the sum probability. Okay, that's correct, Elisha. So, but you can write it as a product, right? We did this last week. So probability of A and B is probability of A times probability of B given A. Do you all agree that this formula is correct? Okay, thank you. But if they are independent, then it becomes what? They're independent. A happening does not depend on B happening. Just multiply them together, right? If B does not depend on A or vice versa, then there's no like probability of B given A is just probability of B. So this is good. This is independence. We are all refreshed. So let's keep coming back. Maximum likelihood estimation. The way we would go about this is that we said, given a distribution, like we said before, distribution, and P of X, and the collection of observed independent data points. This is key. We have to assume that X1, X2, and up to XM, they are not dependent on each other, right? The probability of observing this data just becomes a product of them, right? We multiply them together. This is what we just did together. This will be probability of X1 parameterized by theta times probability of X2 up to probability of XM. And you can just look at them as a product. Okay. So the basic idea of maximum likelihood estimation is that we find the parameter that maximizes the probability of the observed data. And this is what we tried to do in the example, the challenge that I gave in the beginning, where we just took all of this density and then we multiplied it together, and we said the one that has the highest product is the one that is more likely to have been generated by that particular distribution, right? So for maximum likelihood estimation, it becomes an optimization problem, right? You want to maximize the product of this, your joint distribution, your joint, the joints that you have here. You want to maximize the product, and it's equivalent to maximizing the sum of the log likelihood. And we will talk about why this is important later on, but it's just easier to try to maximize this sum log than the product, because as you can see from multiplying 0.001 times 0.000 something, that it becomes the products would start to vanish. It starts to tend towards zero very quickly than the sum. So this is just the idea, basic idea for doing that. So, and to now find the parameters that maximize the probability of the observed data, we look at the different ways of fitting the parameter, right? Like the one way to do so is that we can just use gradient descent that we've known before. That is another way of finding or fitting parameter. But in this lecture here, we are looking at the maximum likelihood estimation. So we will do the standard way in which we're trying to maximize. We do some differential equation. We have some function, and then we try to find the minimum or the maximum. We set it to 0. It's the standard way of which we want to maximize, and then we'll go into this a bit further in the slides to come. So I have another question for you. What kind of distribution is this? By the way, there's a lot of quiz in this class. It's just every now and then I jumped into a quiz. So what is this distribution? You said Poisson. Is this a Poisson? Maybe. Does anyone else think this is a Poisson distribution? Bernoulli? No, this is not a Bernoulli. Normal. This is not a normal distribution. Okay. Thanks, Damilola. Yeah, it's not a Gaussian distribution. So we talked about Gaussian. You already saw Gaussian distribution, right? Let's go back. Gaussian distribution looks like what we saw earlier, like something like this. This is a Gaussian distribution. It goes like this, right? So it's not a Gaussian distribution. It's not Poisson distribution. It's not Bernoulli distribution. So this is a uniform distribution. Again, this is just helping you get familiar with this different distribution. It takes a lot of time, and the more you interact with it, the more it makes sense to you. So if you never work with it, it's maybe difficult to just no, but it's uniform because if you look at this, if you want to compute the probability of A, if on your y-axis you have the probability or PDF or CDF, the probability of A is the same as the probability of B. So it's just uniform distribution on a straight line. And in a lot of scenarios, this is actually also quite common and very useful distribution to know about. It said, is Gaussian the same as normal distribution? Yeah. Gaussian is normal. Statistician here could may not agree with me if I say normal is Gaussian, Gaussian is normal, but normal distribution, like it's a Gaussian distribution that has been normalized, if you can put it that way. So it's like, it's the same essentially. It's also known, Gaussian is also known as normal distribution. So now that we're talking about, I type Bernoulli and erase. Now that we're talking about Bernoulli distribution, right? So we can come back and then I'll show you Bernoulli distribution. So from last week, we talked about if you want to model the probability of success or failure, this is what a Bernoulli distribution tries to do for you usually. So it's binary. It's either 1 or 0. Can everyone remember? So what is the probability that you attend AIS de Lagos Cohort 8 classes and earn a certificate or not? It's binary. It either earn this certificate or not earn the certificate. So the way we do this is that we can learn the parameters of this distribution, which is denoted by phi here, and probability of x equals to 1 would be like phi, and then the opposite would be 1 minus phi, because probability needs to sum to 1, and this is a discrete probability distribution, so it can only take on 0 or 1. It can also be written like this to make it clearer. And visually, this is what the Bernoulli distribution looks like. It's not so if you have probability of 0, then like if you look at the blue one, then it's like 0.8, and probability of 1 is 1. So I guess if you have probability of 0 equal, like if you have equal probability, then maybe this is why you may think it's that what we had before is Bernoulli, because then you have equal probability, right? For 0 and for 1, that would be 0.5, and then it's also uniform. Maybe this is why. Is this why some of us thought it was Bernoulli? So, but in general, uniform distribution is just used to model event that has the same probability of occurring, right? So probability of head or tail, then you can think of it as a uniform distribution, but it's also like Bernoulli in the sense that it has a binary outcome. So yeah, terminology is Bernoulli uniform. It's we can keep thinking about it. So, but here, if you look at the red one here, see probability of x equals to 0 is what? Is 0.2, right? And probability of x equals to 1 is 0.8. So it's either 0.8 or 0.2. It's always binary. All right, and you can write this more compactly like this, which you would see a lot of this. And it says the same thing. It says that if you have, like, if x equals to 1, right, this part here holds, then this part does not hold, right? So what happens if x equals to 0? Let's say success is modeled as 0. If x equals to 0, then we have 1 minus 0, right? And then it means that we would only have 1 minus phi, anything raised to power, like 1 is like 1 minus phi, then phi raised to power 0 would be 1. Anything raised to power 0 is 1. So this does not hold, this would hold. And if x equals to 1, then this would not hold, this will hold. So it's just a way to write it much more compactly. So if we wanted to now estimate the Bernoulli distribution, then we can say that if we have some observed data, let's say x1 is 1, x2 is 1, x3 is 0, x4 is 0, and x5 is 1, right? So if to estimate phi, what do you think we can do? We just said that is the probability of success, probability of failure. How do we compute that? What does it mean in layman term? So what is the probability of 1 in this data set? 3/5. And probability of 0 is what? 2/5. Exactly. So if we can just put that, what you just did mathematically, let's just put it down. What you just did is that you just said we can estimate the parameter of this data, right? This observed data, by just counting. We just count the number of 1 this is the sum of all of the ones divided by the total. Very, like, it seems very obvious, right? So let's think about this. Well, what does this mean? We're saying that if we just know this estimate, this 3/5, that the probability of success, we can model this data set. We can regenerate this data set by just knowing that estimate. This is what it means. So we can forget about this data set and try to generate new data, new ones and zero, given this probability. And you see what in a few slides, I'll show you how you can think about this in that way. But this is not the only way we can estimate, right? What about if you just add 1 to the numerator and add 2 to the denominator? Does the estimate change? Does it change? Can anyone do the math? The probability of success, what is it now? If you add 1 to the numerator and add 2 to the numerator, what is the probability of success now? So it becomes 4/7. Yeah. So, is it a good estimate? I mean, before you had what? You had 3/5, right? So is it good? Is it bad? Can you tell? So this 3/5 is a better estimate. It's bad. Well, hard to say, but we can now figure out how to make sure that the estimates that we actually come about is the best possible estimate we can think about. And this is the job of the maximum likelihood estimate. So instead of us just guessing, what if we had 1, or we can say add 5 or something like that and divide by 10, does it change things? So so we can think of likelihood for Bernoulli by try to maximize this likelihood to help us get the best possible estimate for the data. And if you just plug in the math here, like it's right now it's just plug and play. This is the probability of x equals to x that we talked about, the compact form, and then we plug it into the formula that we talked about before, the sum log likelihood, and we try to maximize this. How can we maximize this? How can we solve this problem? What do we do? I've hinted at it multiple times, but if I want to find phi through maximization problem, usually what do we do? What's our go-to? We've done this multiple times in different contexts. Well, differentiation, right? Oh no. What's like the probability of 0? So we just differentiate. We differentiate the function. We differentiate this, and then we set it to 0. And like we do that because we know that this is convex. There's always a maximum. Like this is a logarithm is usually so it's concave right now. So there that there is a maximum, and you can find it by using like through calculus, through differentiation. So this is what we will do very quickly. So we take this, we maximize this, we take the derivative with respect to phi. And once we do that, we will get this here. So the derivative log of phi, if you find the derivative of that, is just 1/phi. These are like things that you probably know from school, or it's easy to just like, what is the log of phi? It's okay. It's like, you just learn it by heart at some point. So it's 1/phi, and then you do the same thing here. So this will give you phi of x/phi minus, because you have to differentiate the inner part here, 1 minus x, this part, divided by 1 minus phi. And if you do the algebra, like by moving things around, like this to the left-hand side, to the right-hand side, we come about this equation here, right? So the estimate that you get when you like you have derived, like from your derivation, the maximum point can be reached by just saying that the maximum like is sum of over your data point of x over m, which is exactly what we talked about before, right? When we did it here, before we got into the math, when we just like looked at this, highballed it, what's the probability of 1? We said is the sum over all of the 1 divided by m. So but you also get the same thing if you look at the maximum likelihood estimate of that. And this is called, this is now the natural estimate, and it corresponds to the maximum likelihood estimate. So if people talk to you about maximum likelihood estimate, it's just like, what is the which of this parameter, which estimates maximize the likelihood of my data occurring. So there's always data happening when someone says maximum likelihood estimate. So you have some data and you're trying to estimate the parameter. So you first assume a distribution, because without that, it's infinite. Like, which one should you choose? Is it uniform? Is it Gaussian? Is it Poisson? It's just like so many things to choose from. But you have to first assume, based on your knowledge, something you know about the data, the process of generate, like some idea. And then you start with that assumption. You see, you assume a distribution, then you try to like maximize the likelihood of that data coming from that distribution. Does that make sense? So where were we? We just talked about how you can now use the maximum likelihood estimation to also get that like like we can solve this problem, and we can use it to get the estimate for our distribution. So you don't need to like to like come up with it like the count. The Bernoulli was very simple because it's just a count, right? But the moment you start moving into some much more complicated distribution, it's not just a count, something that you can just eyeball and say that probability of 1 is 3/5, probability of 0 is 2/5. Okay, yeah, this is now your phi estimate now, job done. So, but you can use this concept of maximizing the likelihood to get this number, this estimate that we just talked about. And we do this a lot. In fact, remember when we were doing gradient descent, this is the same thing we do. At some point, we differentiate our loss function. We always differentiate, and then we try to try to back propagate by looking at the weights that we had before and negating it from the one that we are computing now. So this is like the whole idea. We are differentiating. We are trying to figure out our way to the minimum or the maximum of a function. And differentiation just provides you a tool to be able to do that. So now, so the question that I talked about, I jumped ahead of the slide, is like how can we sample new data from Bernoulli? If we have this estimate that is phi is 3/5 that we computed earlier, if we want more data from this distribution, we can just generate new data. What do? Well, you can use this code. You just say sample 1. If you generate some random number, like using some randomization, any random number in the universe. So this random number is between 0 and 1. So you know that it's always between 0 and 1. So you just sample 1 if this random number is less than 0.6. Otherwise, it is 0. So this is like, if you think in terms of biased coin, a fair coin would have a probability of 0.5 head tail, but here, like, probability of success or head is 0.6. So it's biased towards 1 than towards 0. So you can generate many new samples by just doing this. Can you see that? Have you done something like this before? Does this look like cool? Let me try it when I get home. Or you're at home right now. It's like, let me try it later today. Okay, so I have a quiz for you in case you're at home and you're with your computer. If you run this code infinitely many times, I mean, this is very easy to do. You just have to wrap it in a for loop. So you have like every time you sample from this distribution, you get 1 or 0 or 1 or 0, and then you save it in some list. And if you do it like a lot of time, let's say 10,000 times, what is the probability of getting 1 on average? 50%. Okay. Anyone else? 0.6. Okay. 1 minus 5. Okay. I recognize that some of us are just guessing right there, but thanks for participating. Caleb is correct. If you do this infinitely many times, the probability of 1 is going to be 0.6. And you can try it out. So this is just also the property of Bernoulli. The expectation over a lot of this sample gets you back to 5. Expectation is essentially the same as a probability. So you can, and if you look at this, it's like 0.6. You will get a lot of different values, but if you look at the mean of it, it should be 0.6. Okay. So let's come back to our earlier example from this Gaussian distribution. Okay. My question now is that what is the maximum likelihood estimation of the mean and the standard deviation of this Gaussian? I know you don't know that yet because we've not done that, unless if you're familiar with the concept of maximum likelihood estimation. But it turns out that if you do that math, the same math that we talked about earlier, where you're looking at the Gaussian distribution, you do the derivative of that, you set it to 0, and you can compute the mean and the standard deviation. It's just nothing but the sum of all of the data. So this is the average. So the mean, the maximum likelihood estimation of the mean for the Gaussian distribution is the average over all of your data. Is also called the mean. And the standard deviation is just also the standard deviation of your data. So my question to you is that, given that you now have this maximum likelihood estimate, which I put up here, this mean and standard deviation, can you try to calculate what the maximum likelihood estimates mean and standard deviation is for your data set 75, 80, and 90? What do you get? What is the mean and the standard deviation of these 3 data, 75, 80, and 90? You just take x minus mean. So given the mean that you calculated here, it's 1.6. So you just, okay. So I think like if you do that, then you can get something about, maybe about 6.2. And this would be corresponding, the maximum likelihood estimate that you get it is closer, like somewhat to what you got like when you did B, right? Like your mean for B is 85. Your mean estimate from your data directly was about 82, and the standard deviation here was 7, and in your data was about 6.2. So the maximum the maximum estimate is actually quite close in terms of the what you get. So we will skip this. This is how you can derive that one for the Gaussian distribution. And we'll quickly jump into the second topic for today, which is called naive Bayes. And it's very simple. Makes some assumption, but works well in practice. And this is the person it's named after, Thomas Naive Bayes, Thomas Bayes, not Naive Bayes. So let's say you have some training data. You have email body. What money is free now, classified as spam. Zico teach Cohort 8, classified as not spam. So the green one is the non-spam email, like your normal email, and the red one is a spam email. So you now want to find out whether or not a new email that you receive is spam or not spam. What are the vocabulary that are in this, like your email body? Can people just list the vocabulary, like the different words that you can find here? Teach, right? What are the words? We have teach, we have now, we have money, yeah, exactly, free, and so on. So we have tool, you have teach, we already said teach, we have CMU 388. So all of these are the vocabulary that are contained in our email body. And our goal is that we want to figure out whether or not this new email, Zico Teach Now, is a spam or a normal email. And how we do that, one way in which we can do that is by using this concept of maximum likelihood estimation, but in the naive Bayes classification naive Bayes classification algorithm. And I will show you how that is done and how those two connects MLE and naive Bayes in this sense. But before we do that, we need to do another recap, which is on conditional probability. And the question is that given two features, X1 and X2, I'd like you to find the joint probability of these two features, that is X1, X2, conditioned on Y. Does anyone know how to compute this? What is the formula for to find the joint of X1 and X2 given some Y? And Y could be your label here. Let's say Y is a spam. Is a spam or not spam? And X1 is like your individual words. Like you want to model money and now given spam. What is the probability of Zico Teach given spam, something like that. Well, if it's not very, like, I mean, like if you don't work a lot with probability, modeling more than one variable becomes a lot. Okay, I see someone already said, that would be probability of y given x1, x2 times probability of x1, x2 divided by probability of y. Okay, we are seeing a lot of probability going on here. All right, so let's go into it. Let's see if this is the same thing as you heard. So you can expand this, right? So you have probability of the joint probability of the three variables x1, x2, x and y divided by the probability of y, which is also called like the marginal probability, like the probability of y. So this is the formula, and you can, cross multiply. You would get that if you want to compute the joint here, you can write it like this: P of x1, x2 given y times P of y. You can write it in multiple different ways. This is one way to write it. And if you keep doing this manipulation, because, intersection is associative, you can move them around. Then you also can get, like, you can rewrite it as probability of x2 given x1 and y, probability of x1 and y. You can break this down even further. You to get probability of x1 given y, probability of y. Do you agree with me so far that this is still the same as this? And then you can just divide probability of y, and it leaves you with probability of x1 given y, probability of x2 given x1 and y. If you want to say that in plain English, like, how would you explain it? So the question is that, given some two variable, let's say Zico and Teach. So what is the probability of Zico and Teach happening, given that this is a spam email? And when we did this, we said it's equivalent to saying that, okay, well, we can break this down by finding the probability of Zico, given that it's a spam email, multiplied by probability of Zico, given that we have observed, like, there is a, like, teach and spam. Like, we have teach and spam occurring. So this is conditional probability. So graphically, we can also explain it in a different way, because this concept is important, and like, understanding it helps you to see, like, why the assumption of independence is very naive, and why it's like it's not the best assumption to have, but it's very convenient in that way. So if you have let's try another example. You have three random variables. So there's a student that passes math. The student also passes history, but there's something that connects both students. It's that that student studies diligently. So what a conditional dependent illustration would look like is this. You're saying that, would say that the probability that the student passes math and the pass history, given that that student studied diligently, is the same as saying that the probability of the student pass math, given that they studied diligently, multiplied by probability that the student passes history, given that they pass math and they study diligently. So like we said that before we can say anything about that student passing history, we need to know that they pass math and they study diligently. This is what conditional is saying. It's the other event happening is conditional on this the previous event happening. So it's like a chain. So this is really difficult as you keep going. As you had more variable, you would have a lot of dependency, and it becomes a nightmare to model this dependency. So what you try to do, or this is what naive Bayes tries to do, like by you try to get rid of the dependency between the two variables x1 and x2. So you assume that passing math and passing history, they are not connected if you know that the student studied diligently. So the probability of the student passing math, given that they study diligently, does not have anything does not change if you know that if you know the probability of the students passing history, given that they study diligently. And in the math world, this is what it looks like. So the other conditional, like where you have x2 given x1 and y, just disappear and simplified to just x2 given y. So the probability of x1 and x2 given y becomes probability of x1 given y times probability of x2 given y. And this is much easier to model. I mean, you can find a lot of, conditional probabilities. It's easier to calculate than having the previous one. Again, sometimes it takes time, and you have to keep revisiting this concept to really get a grasp of it. But I just put it here because I thought it's important to have this intuition, because we talk a lot about independence, conditional independence, and like, what does it mean? How is it different? So yeah, you can always go back again, or we can come back to it. So let's try to do like model this spam behavior using naive Bayes modeling. To do that, so we need to introduce like the setting. So naive Bayes, like I mentioned, is a machine learning algorithm, and it heavily relies on probabilistic modeling. This is why we keep talking about independence, probability of joint, what is the marginal, because this is all this algorithm. This is the core of it. It's probabilistic in nature. So the basic idea is that we have to model the input and the output as random variable. So in our example, spam example, the output would be like the y value, probability, the spam or not spam. So we are going to model that as a random variable, maybe something that can, like we know a distribution that can return true or false, spam or no spam, success or failure. Does that sound familiar? Bernoulli, right? So we could model such behavior with like a Bernoulli distribution, for example. So, and we also do the same for each of the variables. In our spam example, this would be like the individual words. So we try to model those words also using some distribution, right? So the words could be like maybe how many like does money occur in the email that is spam or not? This is now like a 1 or 0. This would be natural for Bernoulli, but it could be categorical. Maybe each of those words could take on multiple values. They could you could have like other kind of distribution that you think to model it. If it is a numerical data, then you would not be talking about Bernoulli or categorical, because you need another distribution, for example, like a Gaussian, to be able to model like a continuous space, because you can no longer count like each individual element as you would do in, say, like a categorical space. So a Bernoulli is like 1 or 0, or binary 1 or 0. If you have multiple variables, you could have like country, for example. You have Nigeria, Rwanda, Ghana. So these are no longer 1 or 0, right? This is now like more like a categorical column, and you need to use another distribution to model this categorical column. So, but let's stay within the realm of Bernoulli right now, because it's simpler to explain, and we've already introduced how you can calculate the estimate the parameter of a Bernoulli distribution. So we just use all of the knowledge we've accumulated so far to solve this a spam classification problem. So I've been talking about like probability. I talked about like we've been saying likelihood or probability of X given Y. They all have name, and the core of this algorithm is from the Bayes rule. And Bayes rule simply says that you can find the posterior probability, which is the one on the left hand side. See here, this is called the posterior probability. It's probability of Y given X, or in our example, it's probability of spam given a particular word or series of words. So probability of spam given money, or given money is 20,000 euros or something like that. It could be. So we're trying to find this probability. Essentially, we want to know if we observe this word, what's the probability of a spam of this email being a spam or not. And it's called the posterior probability, right? So then this is calculated by looking at the joint probability of X given Y times probability of Y, or like you have like the condition, like this conditional probability. Some people call it likelihood. So what is the likelihood of each word given that the email is spam or not spam? And you now multiply this by the probability of Y, which is, in our example, what's the probability of this email being a spam or not spam. It's also called prior probability. You get this for free, and if you have 5 emails and 3 of them is spam and 2 is not spam, probability of spam is just 3/5. Probability of not spam is 2/5. So that is your prior probability. And once you now have this, you divide it by the probability of X, which is called the evidence. And this is one of the hardest things to model, but you can simplify it as just the sum over the likelihood of Y, X given Y, and probability of Y, which resembles like what you have here on top. So just to reiterate, the denominator is just the sum over all of the values of Y of the distribution, and this is specified by the numerator. So like for now, we will just leave it and we just focus on this the conditional and also the prior here. So, and we already talked about the terminologies like prior, likelihood, posterior. I'm mentioning this because you will see it in different contexts, and my hope is that you can map it, and like you always come across this concept. So like you can as well start now understanding it from here. So modeling the full distribution for high dimensional X is not practical. Does anyone know why? Like some intuition why this may be difficult to as you have high dimension? Do you have intuition why, if you want to model the full distribution probability of X given Y for high dimensional X, think about machine learning now, like your features, X1, X2, X3, X100, X1000, X1, 100,000. Some features are as high as that. So so it becomes very impractical to do so, because you would the possibility is just enormous. So let me give you an example. If you have your variable X1, like let's say you have just one X, and X can only take on two values, 1 or 0. If you have 10 of those 10 of those X's, what is the, like, how many values in total would you get? We talked about this briefly in previous class. This would be 2 raised to the power 10. So because so the question again is that if you have a variable X and the variable can only take on two values, 1 or 0, and I'm asking you that if you now have 10 of those variables, like X1, X2 up to X10, in total, how many probability values, or like how many values would you possibility would you have if you want to express that? So you can have for the first one, you can have 1 or 0, like 0 or 1, and then you multiply it by the other one. Like you can have 1 1 1 1 1 1 1 up to 10, right? You can have the second one will be 1 0 0 0 0 0 0 0 0 0 0 0 0 up to 10. So like you can just continue to have that. This is just a lot of possibilities. So what you would have eventually is like 2 raised to the power 10. If you do like a very simple example, if it's just like two variable, this would be 1 0 and 0 1. 2 raised to the power 2 is 4. So you only get 4 possibility. If you have 3 variables, it will be 1 0 0 0 1 1 0 1 0. Just keep going like that. 2 raised to the power 3 is what? What is 2 raised to the power 3? 8. See? So now increase it. If you have 4 variables, 2 raised to the power 4. 5 variables, 2 raised to the power 5. So think in that dimension is just enormous. So it becomes very like large. Possibility is just overwhelming. So this is why you need to make assumptions if you want to be able to solve this problem. And the assumption that Naive Bayes makes is that instead of you modeling that dependency like X1, X2, X3, like given, then you don't do that. You assume that they're independent, what we were talking about before. So you just have the probability of X, your word given spam, is just the product of the like individual conditional. So X1 given Y, X2 given Y. So if you have a word that is Zico teach now that we just find what is the probability of Zico given that there is it is a spam times probability of teach given spam times probability of now given spam. We compare it with probability of Zico given not spam, probability of teach given not spam, probability of now given not spam. And whichever is higher, we say that would be the likelihood. You remember likelihood, which of these two is higher, then this will be the probability that we go with. whether or not it is spam or not spam. So let's quickly go through the rest of this slide. So we just said that it is naive because of this assumption that it's assumed that each of the features, they don't influence one another, which is not usually true. You can have, like, for example, if you have two features like cash and money, would you say they are not influencing each other? Cash and money are like synonyms, right? So it's like there is a dependency between them. Like if you have email that has cash and you classify it as spam, it's very likely that the same email that has money is also maybe some spam. I mean, given other words, of course, like that's I've been seeing in a lot of spammed email. So, but despite the simplicity of this assumption, it works really well in many situations. So Naive Bayes is really good to know how it works. So let's come back to our example. If we wanted to represent this in a machine learning form, right? It's like one representation could be like this. So you just take each of the vocabulary here, it's become your features. So you lower cases, CMU 388, cohort 8. So every word that you find, you just tokenize your sentence, and then you find you disregard duplicates, and then like all of the words become your features. We did this in the natural language processing and text class. I'll just say a quick recap. So this, once you have this, you now say that for each of wherever you find, like if the word exists in the sentence, you just give it a 1. So right now, cohort 8 exists here, then Zico exists, it's a 1. Teach exists is a 1, and the class is spam, it's not spam. You do the same thing. Money exists here, money is a 1, ease is a 1, free is a 1, now is a 1. The rest of the features are turned off. They don't exist. You cannot find them, so they are turned off. So, and you just do this for all of them. So now you have a data set with rows and column. You know how to do this already. You can use any machine learning algorithm to solve this now. You just learn based on this data, and once you learn the model, you can make your prediction. In fact, you can also use like sklearn multinomial naive Bayes to solve this problem as is right now and get the answer. But that would be boring, right? We are here to learn about how this sklearn like this multinomial naive Bayes, how was it like designed, or like what is the implementation behind it? So let's do some math to make it interesting. In order to do the math, so we need to model individual distribution like we talked about. So we will assume that we need to assume a distribution for each feature and also for the label. So I have a question for you. What distribution does this look like? We've been talking a lot about this distribution. I'll keep asking until it clicks. What distribution does this look like? Like for just focus on this one row, one column here. What distribution does this look like? What kind of distribution can we use to model this row? This Bernoulli, yeah, it's just 1 or 0. We've been talking about Bernoulli. It seems like I will not let you rest with Bernoulli, right? So this looks like you can just like maybe model this as a Bernoulli. Model this as a Bernoulli. It's just 1 or 0. Bernoulli. In fact, everything can be modeled as a Bernoulli. Products of Bernoulli. So you learn a parameter here, Bernoulli parameter. Another parameter, phi2, Bernoulli parameter. So each of these feature has a Bernoulli parameter attached to it. And if you have a new data, what do? Well, you find if the data says like money, you take the Bernoulli parameter of that data, and then you multiply and you get your answer. You will see what it means in a few slides. So like we said, we need to specify a distribution, and we just eyeballed our data set. We find out that we can use Bernoulli for it because 1 or 0, right? We just use Bernoulli. We also we do the same thing, right? Sorry, so much. We do the same thing for this is the Y, the label, spam or no spam, and these are all of these features, the words, right? And so we assume, like we already said this, we just assume Bernoulli. So we can move on. So now we are trying, the things we need to learn is the probability of Y. That is, this is the prior probability. Remember, probability of spam or not spam. And the second thing we need to learn is probability of each word occurring given that this is a spam, or the probability of each word occurring given that it is not a spam. And this is what is this called? This is the likelihood of each word given spam, likelihood of this word given not spam. And all of this thing that we keep attaching to it is just to tell you that this is a probability distribution. I know it makes it much more like intimidating, but it's just to be explicit that this is a probability, like this is a distribution. This is why we keep putting the parameter thing there. So to estimate this parameter, we already know how to do this. We've done the maximum likelihood estimate of Bernoulli in the first part of the lecture, which we said is just the count, right? So we count every time we see 1, we count it, we divide by total. And for the conditional, we do it a little bit different because now we are conditioning on a part of the distribution. So it's no longer the entire thing. We only look at when you are spam. This is what this equation is telling us. We say that if Y equals to 1, that is, we only care about spam. We count everything that is in spam spam. If that word, if that word occur, we just sum it all up. We'll say what it is. Like, this is just math. Then we'll say what it is when we look at the example, when we try to solve it. So we sum every word that is spam, like every time the word occur in a spam email, we sum it all up. And then we divide it by the total words in that spam email. We do the same thing from non-spam. Then this would be the likelihood of the word coming from spam or not spam. So if we now know this parameter, it's the rest of our job is easy. To sample, to predict a new data point, we just need to take the prior probability, probability of spam or not spam. We take it, we multiply that prior probability, this one, we multiply it by the product of the other one that we talked about. So this is just trying to compartmentalize the form. If we break it down, if spam is in the email, this will be 1. We'll only care about this part. If spam is not in the email, this will be 1. We'll only care about this part. So I'm just trying to explain what this formula means. It's the same thing that we've been talking about. Just multiply the condition that we add by the prior, and then you will get the probability of the new data, the product of the new data given probability of the new data, the new data being spam given the word is changing, probability of spam given the new data English. So after you have computed the right hand side to get the desired probability, you can also just divide it by the evidence. You remember this thing that I told you to pause on for now. So it's just the sum over all of the Y value to get a complete probability. But if you just want to see if something is spam or not spam, you can simply look at the maximum between the two. So we can quickly do this exercise. I think this is important because this is now going to solve the problem that I posed earlier. I also provide a solution, so you can also just go do it by yourself. Can you see can you see this? Yeah. the spreadsheet. Okay, so let's quickly solve it. Oh, I've already showed you the solution. So I said if we wanted to solve it now, we need to start with things like the prior probability, right? How can we compute the prior probability? Can anyone remind me of the formula? So the formula for the probability of spam, what do we do? We just sum everything here, right? And then divide by the length of this. Is it length? Is it not length? What is it? Is it not length in, sorry, I just used Python. Is it count? I think it's count. Okay, great. So we just sum everything. Probability of span is 3/7, right? You can also confirm it. 3/7. See, it's the same. But we're going to use Excel because we are computer people. We can do Excel. Excel can do the math for us, so we don't have to do it one by one. And the probability of not spam is what? What is it? Anyone? One minus, thank you. 1 minus spam. So this is 1 minus spam. So this is like 0.5. So these two are our prior probability. Can you remember? Prior probability. So once we compute the prior probability, remember, let's come back here. We need to do it one by one. We need to first find this prior probability, and we just did it by computing this formula. We sum everything up, we divide by m. So this is the first thing we do. So the next thing we need to do is to do this formula here. So what is that formula saying? So we are trying to compute what is the what is the probability of the word, each of this word given that is spam, and what is the probability of the word given not spam. And to do the same thing, we can just say the probability of the word given the spam will just be the sum anytime the word occur. No, this is not the. So anytime the word occur in the spam email, right? Divided by what? We want to calculate the probability of the word given spam. So we sum, we look at every time the word occur in spam. CMU388 did not occur at all. Someone said we need to divide by 0.42. We need to divide that by the probability of spam. Do we all agree? This is not like this is not true. We cannot divide by the probability of spam. So to compute this probability would be like sum everything and then you divide by the number of words in spam. So not the probability of spam, it should be the number of words in spam, in the spam email. So to do that, we can just sum all of the words in the spam email. And this is 0 because, I mean, like these words did not occur in spam. And we can also do the same thing for this here. We try to find the sum. And we divide it by the sum of everything here. So and this so because this word occur in not spam, so you see that you have a higher likelihood of the word in not spam than in spam. And you can just do the same calculation for everything here because we're using Excel. We simply can make it easier. So we just do the same. So if you look at it, it's always like we try to sum everything here. and divide by everything here, and we do the same thing for that one. And we also do the same thing here. Let's see. So everything we have here is now the probability of each word occurring in spam. So cohort 8 did not occur at all in spam, so the probability is 0. 3 did not occur, 3 occurred in spam, so the probability was 0.18. And we can keep doing like when we now do this to now what I just computed is what we have here. And to now calculate the new one, the like whether or not something is spam or not, we just multiply each new word, like the word that we have here now. We look at the now for spam, you multiply it by teach. Where is teach? We multiply it by Zico, and then we multiply by probability of spam. So this would give you the results for probability of Zico given spam given Zico, and then you can calculate the same thing. You can calculate the same thing for probability of spam. Let's see, let's quickly do this. So now is here times Zico times teach times not spam. So you have these two probability, which you can turn into probability density. This will be this plus this. So this is now your final probability. I know it seems like I'm rushing through them right now, which is true, but we can always go back to it at some point when we have time. Sorry, this is not correct. B2 B25 plus. Okay. So yeah, so now if we want to predict if this is spam or not, we just need to say that if this is greater than this, then it is spam, but it is not greater. So we can just say this. So it is not spam. This is how like you do by naive Bayes on spreadsheets. But of course, like you can always use do it using multinomial naive Bayes, which I also did in another notebook that I'm not showing here. But I hope that the concept of naive Bayes spam classification is clear. So for this example that we have now, the probability of Zico teach now is less likely to be a spam. So we would classify it as a normal email. Yeah, I just wanted to breeze through some potential issue, which was with the, like, you have precision. We already talked about this. If you multiply a lot of probability, it starts to get to 0 quickly. And the way you combat it is this logarithm that we talked about. You just compute the log. And also, if you have never seen a word before, the likelihood of that word occurring will simply be 0. So for example, if CMU did not occur at all in your spam email, then it's 0. And sometimes this is not desirable because it becomes like 0. If you multiply 0 by another probability, you don't get any signal of maybe there is a very small probability mass. You are just not capturing it. So to combat this, some people would do something like Laplace smoothing, where you add 1. So you assume that you've seen each word at least one time. So you add 1 to the numerator and you divide. You try to cancel out this effect by adding 2 to the denominator. So yeah, you can also use other distribution to model this. We've used Bernoulli, but you can use multinomial distribution if you have more than one like variables. So if it's no longer true or false, like each of your features can take on multiple variables, multiple categories, then you have to use order distribution. If each of your features is a numerical, it's continuous in nature, then you cannot use Bernoulli anymore. You would want to use something like a Gaussian and so on. So we didn't cover like this using order distribution in this lecture, and we also did not cover like this the like machine learning doing machine learning via maximum likelihood. So there's a natural connection between the different loss function that we've seen so far, like your logistic loss or your mean squared error. You can also write them in a way that they're maximizing the likelihood. But you can look at these two resources, which is what I based my slides on from the CMU course, taught by Professor Zico Coulter, and now Pat. So other resources to understand how Naive Bayes Classifier works, you can look at this Louis class. It's amazing. Louis is one of my favorite YouTuber. He just explains things in a friendly version. So you can look at that, and you can also look at the video from Josh from Stats Quest. It's also usually a good video, very exciting because there's a lot of animation, and you can understand it a bit more, less mathy. Yeah, this is everything I have